All right, good afternoon, everybody. Welcome to class. Let's get started. All right. We're gonna wrap up two-port networks today. We just want to look at interconnection of networks and just broadly how we can use that which we have looked at so far in terms of circuit analysis. I see that quite a few persons aren't here as yet, but we will proceed. We shall proceed. Okay, so let us start with some definitions. Can I get a volunteer? What do we mean when we say that we have a series connection? What do we mean by that?
Sir, that component.
Go ahead.
The current leaving one element is equal to the current entering another.
Yeah.
All right, we'll be a little more accurate to that. That's not exactly how we stated it. Be a little more accurate.
So the current entering element or a terminal is equal to the current leaving terminal of the element and entering another element.
All right. Let me hear you, Mr. Peru. I don't know if that's what you were going to say. Peru or Odian, who was it?
Oh, yes, sir. It's Subi, sir. I was going to say that basically the same thing, sir, saying that a series connection is a connection where an element is connected in such a way that the current leaving one element is the same current entering.
No, that is different from what was said earlier. So the current leaving one is the same current entering the other. That's quite different from what was said. All right. So in terms of parallel connections, when we said two elements are connected in parallel, what do we mean? Come on. Yeah, just finished networks one. That's the reason it's a prerequisite.
The current entering a node divides between branches.
Start that again, Mr. Morrison. Assume that I don't know what you're talking about. You say a lot of correct things, but I mean, I don't know what you're talking about. Come again. So, Morrison?
Yes, sir.
Yes, sir. Just rephrase it so that it is clear to someone who wouldn't have done the subject before.
Total current entering a node divides between branches.
All right, so what do you clean that up from? You see, you know what you're talking about, but I want you to state it in such a way that someone who did not do this thing before would understand.
Sir, it's a circuit configuration where the current share between branches.
What do that mean? What I mean by branches? I'm asking about when you have two elements in parallel, what does that mean? When you say that they are in parallel, what does it mean? Give me a complete statement that describes everything.
Sir, that means that the branches have the same voltage and different currents passing through them.
That don't help us.
May I attempt?
Go ahead,
So,
man.
when there is a parallel connection, it means that the voltage across each component.
That's what Ms. Campbell just said.
Okay, and in reference to the current, sir, the current between them are going to be shared based on the current entering the node.
Well, that's what everybody just said before. All right, all right. All I'm simply looking for, in terms of a complete statement that would help someone who has not done the subject, is that the current entering the node, connecting the two elements. You just tell me two branches. Which two branches? I don't know what you're talking about. We need to be able to express ourselves in a way that makes what we are saying clear, to especially non-technical people. And this is one of the strengths that an engineer should have, right? Because whilst you're going to deal with the technical stuff, you're going to be limited by the accountants, yes, the financiers, who don't understand the technical. So you need to be able to break it down in such a way that they will understand. So communication, that's why you do so many English courses. All right, so it is that the current entering the node, connecting the two elements, divides between them. All right? All right, now,
Yes, sir.
we have that clear. In terms of series connection, current leaving one is the same current entering the other. Can be equal, but not necessarily the same. Yes? And then we have the definition for parallel. Now we're going to use those definitions when we look at two-port networks. We're going to stick scrupulously to those definitions. So here I have two networks. I have network A, and I have network B. Let me use a different color for that. Right? So I have network A, network B. All right? So draw these from the place. Let's look at all of this that we have here. All right? That which I have just outlined. That would be the network. So that's the single network. What we have a port here. We have a port here. So we have an input port with V1 and I1, and we have an output port with V2 and I2. Within this network, we have two networks, network A and network B. All right? Now I want to look at the current I1. So here is I1. I1 comes to this node and it divides. So we have I1A going to network A and I1B going to network B. If we go on the output side, we have I2, we have I2A going into network A, and we have I2B going into network B. Everybody see that?
Yes, sir.
Yes, sir.
Now, if you look at the voltages, here you have V1. Now, V1, as we know, voltage, difference in potential between 2 points. So V1 is the voltage across those two terminals. And the terminals continue. So we'd have the same potential across that. So in other words, V1 is equal to V1A. And if we look at V1B, again, here's the voltage. There are the terminals. We'd have the same terminal voltage here. So V1 is also equal to V1B. And we can see the same thing for V2 and V2B and V2A. So the two networks, network A and network B, what we have is that at the point where the two networks are connected. So at that node, we have the currents dividing. At this node, currents dividing. And the voltage between the terminals would be the same. So in essence, what we are saying is that these two networks are connected in parallel, based on the definition, based on what we know of parallel networks or parallel connected components. All right? So it comes back to some of the things I was emphasizing back in networks where I told you, you can look at just how the element is drawn. You must always use the current reference to make certain determinations. All right? So we see that these are in parallel. Is there anybody who is unsure about it? All right.
Sir,
Yes.
just in regards to the voltage, the potential difference, is it that the V1 and, as I say, arrows and V2, but I don't see any for V1. Is it safe to assume that they should be in the same direction?
Pardon me?
It's safe to assume that sir, I see on one terminal.
Look where the black lines are. Look at the black lines.
Yes, sir.
All right? Look at the red lines. They are coming from the same terminals. Remember, there is no voltage drop across the connecting wires. Eh? So therefore, the potential difference between the 2 points, these 2 points, would be the same up here, so same potential difference, same potential difference. So the voltages at the input are the same, and the voltages at the output will also be the same. So it means that we have a parallel connection.
Yes, sir.
All right. So with that said, if we just write our equations for network A, sorry, and the equations for network B, just excuse me a sec. All right, so these are our 2 sets of equations for networks A and network B. Networks A and B, sorry. All right? So based on what we just said, in terms of them being in parallel, I1 is equal to I1A plus I1B. Yes? And for the voltages, V1 is equal to V1A, which is also equal to V1B. That's what I should be referring to. And V2 is equal to V2A, and it's equal to V2B. So wherever I have V2A and V2B, I can substitute V2. Yes? And similarly for V1, that's equal to V1A and V1B. So where I have V1A or V1B, I can substitute V1. All right? Always bear in mind that this is the network that we are considering. Let's call that network C. So network C is a combination of A and B. All right? Okay, so the voltages are the same. We established that already. Similarly, we look at the current. So I1 is equal to I1A plus I1B. Yes? All right. Similarly, I2 is equal to I2A plus I2B. All right, so we're just establishing these bits of facts based on the network connections that we have. Okay. So if I then, based on the equations that we looked at, based on these equations, if I now combine them, I have I1 being equal to I1, or this should be I1A plus I1B. So this subscript here should be A. Similarly here. Let me correct that.
Did you resume the record? All right.
So simplifying, simplifying. I therefore have I1 to be equal to Y11A, Y11B times V1, etc. In summary, for networks that are in parallel, the overall admittance parameters will be given by YA plus YB. All right. So that's for parallel connection. So we can now look at series connections. Again, we go back to the basic definition. The current leaving one component is the same current entering the other. So if they are in series, current leaving one is the current entering the other. So let us put the same two networks, networks A and B, in series. So draw this one, please. Okay, so why do we say that these networks are in series? We see I1 entering network A, yes? So I1 is equal to I1A. Now, we know that, in any port, right, in any port, the current that will enter one terminal must be the same current leaving the other terminal. So it means that I1A would be leaving the lower terminal of port 1. Is there anybody who disagree with that or is unclear on that?
I never heard what you said, so
Pardon?
some noise in my background, so I never catch what you said. So.
The current entering one terminal of a port will be the same current leaving the other terminal of the same port. So if I1A is entering the upper terminal, it's the same current leaving the lower terminal. Based on the connection, this is the same current that will enter the upper terminal of network B. And by definition, the current leaving one element being the same current that enters the other element means that the two are in series. So we come back to the definition. All right? So it means, therefore, that networks A and B are in series by virtue of the current flow. If we look at the voltages, the voltage across port 1, let me remove some of this ink. The voltage across port 1, which is this, yes, is going to be equal to the sum of the voltage across port A, 1A, and 1B. So V1 would be equal to V1A plus V1B. Again, within an closed loop, yes, we know that the algebraic sum of the EMFs is equal to the sum of the voltage drops. So we would have a closed loop in terms of our port. Voltage drop across here plus that is equal to V1. Similarly, at port 2, 2A and 2B, when summed, gives us V2. Also, 2A going into network A would be 2A coming out of network A, which is the current entering network B. All right? Yes, Mr. Haynes.
Sir, so the voltage drop, so V1 would be equal to V1A plus VAB, or are they all the same? That's what I'm trying to. Would the voltage drop, V1A and V1B be equal to the sum of them? Would the sum of them be equal to V1?
Yes.
Or,
yes.
Okay. I thought they were all the same thing a while ago. All right, thanks, sir.
Okay. So if we just put those in an equation, again, using the impedance parameters, we have the sets of equations for both networks. So V1 and V2 for networks A and B are written as shown in terms of the impedance parameters. And using the same analysis as before, using the same analysis as before, we have that I1 is equal to I1A plus I1 equal to I1A, which is equal to I1B, and I2 is equal to I2A, which is equal to I2B. And for the voltages, V1 is equal to V1A plus V1B. V2 is equal to V2A plus V2B. So wherever we have I1A or I1B, we will just substitute I1. Similarly, for I2A and I2B, we'll substitute I2. And then, of course, based on what we have here, in terms of the voltages, we will add the two equations. So in adding the two equations, and making the necessary substitutions. So I've just skipped out 2 lines from what I did with the admittance, but you already would have seen the approach taken for the admittance. So in summary, if we have 2 networks in series, then Z is equal to ZA plus ZB. All right. Now, the connection that we did not look at in terms of networks 1, but will feature quite heavily in your experience as engineers, is that of a cascade connection. And cascade simply means that the output of one system is the input of the other. All right, that's basically what cascade looks like, which is why it's important that we make the distinction in terms of series, because series and cascade, can be confused, but they are quite different. So for your cascade connection, the output of one is the input of the other. So this is our cascade or cascaded networks. But in all that we are doing, students, please note that the combined network, yes, what we call network C. Network C is a combination of A and B. All right, so take this, draw this. All right, so we're gonna go a little slow with this one. So just like what we did with the parallel and the series connections, yes? We want to look at which parameters or currents or voltages are the same, so to speak. So I'm going to take you from the input through to the output. All right? Now we can't take any shortcuts here. Just going to look at this carefully. We're going to focus firstly on the currents. So I have to look at the currents. So we're going to be looking at the upper terminals. I1 is equal to I1A. All right? Now, if you look, remember the convention needs to hold true. Whereas we're meaning that at the output port of a two-port network at the upper terminal, the current is going in. But also on the input port, it's going in at that same terminal. So at the top here, between the two networks, I2A would be equal to the negative of I1B. Or you can say it the other way around. I1B would be equal to the negative of I2A. The reason for this, or the reason we have to say that, is because there's only one current that is flowing. All right? So there's only one current, but we know that by convention, the currents must be entering the networks. So I1B is equal to the negative of I2A, or you want to say it the other way around, I2A is equal to the negative of I1B. And then we come to this section of the network, and we see that I2 is equal to I2B. So we go to the currents. All right. For the voltages, V1 is equal to V1A. So V1 is equal to V1A. V2A, on the output side, V2A is equal to V1B. And for network B, V2B is equal to V2. Now, I'll tell you up front, so far we have looked at the admittance parameters for parallel circuits, parallel networks. We have looked at the impedance parameters for series networks. For cascade connections, and I hope you're hearing me because the rain is pouring outside. For cascade connections, we use the transmission parameters, all right? So we write the transmission parameters for both networks as shown. Go ahead, please. Apologies for that long delay. All right, let's get going again. Okay. So as I said, we're going to go a little slow with this one because it is not as straightforward. Remember, going back to this, remember V1 equal V1A, V2 equal V2B, I1 is equal to I1A, V1B, V2A, etc., etc. So here we now have the equations for both networks, yes? With these equations, we're now going to make some substitutions based on what we just said. So, just reiterating, V2B is equal to V2, I2B is equal to I2, V1A is equal to V1, and I1A is equal to I1. And then the V1B is equal to V2A, and I2A is equal to minus I1B. So these are the key substitutions that we are going to make.
Sir,
Yes, Mr. Thompson.
sir, do you have a generalized definition for cascade networks, like we had one for series and parallel?
I gave it already, sir.
All right.
All right. So I'm now making the substitutions, bearing in mind, students, that for transmission parameters, it is the input voltage and current with respect to the output voltage and current. Yes? So V1, which was equal to V1A, yes, we're making that substitution. And I1, which is equal to I1A, we're making that substitution. All right. Similar V2B, we're substituting for V2, and I2B, we're substituting for I2. All right. Okay, so this is what we have here. We're going to be using these relationships in determining our final relationship. So we make the substitutions. ABV2 minus BBV2, that was equal to V2A, because remember we said that V2A was equal to V1B. That's up here. V2A is equal to V1B. So where we have V2A, we are substituting V1B. All right? Also, I2A was equal to the negative of I1B. So we have I1B here, and it's equal to the negative of I2A. So we can make those substitutions. So that's what we have done. So for V1, all right, so we're dealing with the voltage first. So all I've done is to expand and simplify with respect to V2 and I2. Again, bearing in mind what the transmission parameters are used to give us. All right, they are the input voltage and input current with respect to the output voltage and output current. Yes? So obviously, what we have here would be the coefficient of V2, and we have here the coefficient of I2. And if I did the same, as we said earlier, I1B is equal to the negative of I2A. We'll make that substitution. All right. And then we get I1. Again, this is the coefficient, and this is the coefficient of V2 and I2, respectively. Now, the relationship for your for these elements will not be as obvious as with the other two that we looked at. Yes. However, there is a relationship, and that relationship. Are we finished with this?
No, sir.
No, sir, that's second.
All right. So if we put those coefficients that I just highlighted in a matrix form, all right, in matrix form rather, yes, then, I mean, again, it's not obvious, but I'm telling you that this is the case. What we have here is really the product of the transmission parameters. So for a combined network, a network consisting of subnetworks in Cascade, the overall transmission parameters would be equal to T, which is given by TA times TB. Okay, so in summary, networks are in parallel. The admittance parameters of the combination is given by the sum of the individual admittance parameters. If they are in series, it's the sum of the impedance parameters. And if they are in cascade, it's the product of the transmission parameters. Again, students, it doesn't matter which set of parameters you have, because you can always convert these parameters, convert from from admittance to impedance to transmission, from hybrid, you name it. All right? That means that in building your systems, if you have your systems connected in series, then you can find the overall operation of that combined system. If you have them in Cascade, you have a two-stage amplifier. You actually have the two stages connected in Cascade. Again, you can combine the parameters to see what the overall operation of the two stages would look like. All right, so this would help you in your systems engineering. All right, so in terms of theory, there's nothing more to say to you as far as two-port networks are concerned. However, application does take some thought, does take some accurate work. So let's look at a couple questions now. Let's start with this one.
Sir, can I ask you a question before you move on to that question?
Go ahead.
In the Cascade network, so you said that V1 equal to V1A, right? What if there was a resistor in at say I1A? Wouldn't that change the equality and make it become?
All right. What is V1? What does V1 represent?
The voltage from I1 to, well, the input I1 to the output I1. So.
Oh, but what does V1 represent? If we're dealing with two-port networks, what does V1 represent?
The input voltage.
The input voltage, yes?
Mm.
So you're saying what if I put a resistor here, so?
Yeah.
Then it means that V1 would be here. Because V1 is the input to the port.
Okay. So it's just so it represents the input to the.
So this would be a source voltage, but V1 is the input voltage to port 1 of the network. So the black box, where am I? The black box is here. Inside here, you have a combination of networks. Out here, this is V1. If you want to connect 1 million resistors out here, doesn't matter. V1 is the voltage at the input of the port. So if you connect something out here, which is a voltage source, you'd have to find the relationship between Vs and V1 and I1. We clear?
Yes, sir.
So what are the admittance parameters of this network? Now, as shown, I think it's obvious that it would not be very easy to analyze the network as shown. But what may be helpful is if we can break up this network. Does somebody want to finish drawing? All right. So it may not necessarily be, something that you would quickly see, but nonetheless, we can draw this as the equivalent network. We haven't changed anything, really. If you look back at the original network, all right? Look back at the original network, current coming here would divide here and here. Yes? What I've done is to redefine or to rearrange the return leg. All right, so if we were to bend this and straighten it back out, you realize we have the same network. Is there anybody who disagree with this rearrangement or is unable to understand or see clearly why this redrawn circuit is similar to the original?
Sir, not seeing it, sir.
So,
It's that I have circled here, Mr. Gill. This line right here, sir. Is there a line on the bus mark?
Yes, sir, I see.
Flatten it. Flatten it. Have you made it flat? Sir Gill. All right. So students, we have two networks. That's my network A. This is my network B. So with these two networks, for network A, those are the admittance parameters. And to allow you to practice, I wanted to find the parameters for network B. All right. Anybody found the parameters for network B? Anybody still in the room?
Yes, sir, we're here.
Network B.
For the admittance, I have y11 is a half. Y12 is a -1. Y21 is -1, and Y22 is 1/3.
Y22 is 1/3.
Yes, sir.
Let's see.
I got 2/5.
Yes, sir, I got 2 of 5 for it. So
2/2. All right, so let us look at the network. There are short circuit parameters, right?
Yes, sir.
Yes, sir.
This one, you short circuit that I are looking in here, which will be 1 plus 2 in parallel with 1, right?
Yes, sir.
So that's 1 plus 2/3, which gives you 5/3, right?
Yes, sir.
Good. So it means that y11 would be 3/5.
Yes, sir.
Anyway, don't worry, it will come with time. It will come with time. So these are the admittance parameters for network B. And for those who did not attempt it, you're not helping yourself by sitting down waiting on an answer. Okay, so based on the fact that we connected them in parallel, it means that we now simply add the two. And so for the combined network, that's the admittance parameters. Any questions? All righty then. So I have the option. I mean, I could look at the network as is. We put it in parallel, but what if we start to redraw the same network? I look at it in series. Again, I go back to the original.
Oh, sir, I wanted to ask a question. I had a thought on the original circuit. You could transform this circuit like into star to delta here.
Yeah, that's if you were going to look at it as a single circuit.
Okay.
So you could convert that. Yes?
Okay.
But you would agree with me, yeah, that's a lot of work for a simple circuit. So this is where, we can put it as a parallel. Hello?
No, sir, nothing.
Okay. Or, going back to the original, if I were to make these vertical, and then this node, I'm going to spread it out. So I can have the node as a dot, which is what we have here, or I can make it into this rectangle. Nothing has changed. Just ensure that I have the 2 ohm connected to it, these 1 ohm connected to it, and that this 1 ohm is connected to the lower terminal. So that's all we're going to do with the next circuit. So rearranging, do you agree that that is the same circuit? Is there anybody who disagrees that this is the same? All right, good. Because this really is the node. And I have just made the 1 and the 2 ohm stand up instead of being horizontal. And by doing so, what we have are 2 networks. That's network A. And this is network B. And based on these networks, we see that the current entering here, however it operates inside here, is of no importance to us. What we know is that this current that enters there is the same current that's going to emerge from that point. And that current will enter network B. So in a sense, we have two networks in parallel, in series, sorry. Because the current leaving one network is the same current entering the other. All right? So, for the impedance parameters, how do we treat with the port that we're not looking at? First of all, let me ask it another way. What kind of parameters are our impedance parameters?
Open circuit.
Open circuit. So without an open circuit, looking into that port. Yes? What would Z11 be equal to? So we're looking into that, into the upper port. What would Z11 be equal to? Come on, folks.
The one in series with one. So there's 1 plus 1 plus 2.
Come on, this is the network we're looking at, you know.
Sir, wouldn't it be one in parallel
with the negative
J2 in series with 2?
All right. So it is 1 in parallel with 2 in series with J2.
Correct.
So it's 1 parallel 2 minus J2. What's that equal to?
Two minus J2 over 3 minus J2.
Since we have that port open, let us look at Z21. Z21, what is Z21 equal to? How do we find Z21? First, it's an impedance, so what are we dividing? By what?
I2 V1.
Voltage by current.
So it's V2 over I2 over I1. And that is with I2 being 0. Yes? So, based on I1, what would V2 be equal to? Are we going to find, what is V2? Where is V2?
Across the 2
Across the 2 ohm, yes. So I have the 1 ohm, I have the J2, and I have the 2 ohm. What is I1? Where's V2?
Across the 2 ohm.
All right. I1, how would I1, what component of I1 would pass through that 2 ohm?
The same that passed through minus J2.
So how do we find that then?
Current divider.
Good. So by current division, let's call this IX. What is IX equal to?
IX equal 1 over
I1 times 1 over
Yeah, 1I1 over
1 plus 1 minus J2, I think.
Over what?
over 1 plus the
Was 1 minus, okay, would be 1 plus negative J2.
1 plus what?
1 plus 2 minus J2.
Which is equal to?
Calculator.
3 minus J2.
3 minus J2. So that's Ix. So what is V2 equal to?
2 times Ix.
2Ix. So it means therefore that Z21, which is 2Ix, would be equal to
2 times I1 over 3 minus J2.
Remember Z21 I'm talking about. With I10, what is Z12? Go back to the circuit. If I10,
V1 over I2.
ah,
ZI2 is V1 over I2.
okay, yes. So what component, where is V1? Where is V1?
Across the 1 ohm resistor.
Okay, so what component of I2 would be flowing through the 1 ohm?
Yes, repeat that, please.
What component of I2 will be flowing through the 1 ohm?
The same as flowing through the negative J2.
Speak up, please. Speak up, Mr. Facey.
The same one that's going to the negative J2.
Which is?
Minus
2I2.
So if we call that IY, what is IY?
Minus I.
IY would be equal to 2I2 over 1 minus J2, or the negative.
Same current divider. So 2I2, it could be 2I2 over 2 plus 1 plus same 3 minus J2.
I want to multiply that by 1, we get the same thing, right? So it means that Z12 is also equal to 2 over 3 minus J2.
Excuse me, sir, question. I've been realizing that on more than one occasion, Z12 and Z21 are most times the same answer. Can we just assume, say, all right, if we find Z21, it'll be the same as Z12?
No, sir.
All right, sir.
I gave you a question the other day to do this stuff from scratch. How many of you did it?
Which one are you talking about, sir?
I said the one I gave you to do from first principles.
Yes, maybe let's find it.
And you did the conversion and saw that they were equal?
Yes, sir.
Okay. Did you get the same values? I said 2, 1, and 1, 2?
No.
No, sir.
Okay. You see, Mr. Facey, you just told me that you didn't do the work.
No, sir, I did it, but I've been seeing more than one occasion where that has been the
Yeah, but
case.
if it doesn't add up on one occasion, why you going to make a law for it?
I get what you're saying, sir. I get what you're saying.
You know, when I was a young boy, I used to say shortcut, draw blood. You hear that one, Mr. Facey?
Yes, sir, enough time.
Yeah, in a network, shortcut, draw grade, or marks, yeah?
And the module itself.
Ah. And Z22 would now be 2 in parallel with 1 minus J2. So that will be 2 minus J4. So you have the impedance parameters for network 1. So for network 2, on it,
For network 2, sir, wouldn't it just be 1, -1, -1, 1?
I don't know. You tell me. So what is Z11?
Sir, just 1.
V1 over I1.
Which is equal to? Huh?
1 ohm, sir.
With I20 meaning we have it open circuited. Where would I1 flow?
Through the 1 ohm resistor.
So what is Z11?
1 ohm.
1 ohm.
Huh?
1 ohm.
1. Good.
1.
With that still in place, what is Z21?
1.
And what is Z12?
1.
And what is Z22?
1 again.
All right. So I'm not sure why you guys feel that you want to, do the speedy thing. It's a school challenge, Just go through it, do it step by step. All right? And get the parameters. So now that we have the Z parameters for both networks, you add them. So you have Z1 plus Z2. And that gives you Z. I then want you to find Z inverse and compare this to the Y that we calculated earlier. It's the same circuit, so both should be equal. This is a question I had asked you to complete, eh?
Yes.
Wait, no, on what I
Oh,
have,
no,
I have
sir, no.
2, 3, 4, 4, 2. So the values are different. Same shape, but the values are different.
Same shape, but it look a little different.
Yes, sir.
All right. So, here is what I'm going to ask you to do. Let me just make sure. I don't want to give you that. Right? All right, all right, all right, all right. We have 12 minutes left. We have 12 minutes left. And you're going to have to write fast, all right? Take this question, please. All right? Okay, so for this network, we're looking at the impedance parameters. Yep. So we want the impedance and admittance parameters from first principles. So with the open circuit, we know that Z11 is equal to V1 over I1, with I2 being equal to 0. So it is 4 in series with 2, which is in parallel with 3 in series with 2. And we simplify that, and we get 38 over 7. All right? All right, 10 minutes, okay. For the transfer impedance, at Z21, similarly with I2 being equal to 0, yes? So with I2 being equal to 0, meaning we have the open circuit, we want an expression for V2 with respect to I1. Now, clearly, you'll see that because this is open circuited, what will be the voltage drop across this 4 ohm resistor?
0, sir.
0. So the V2 will be seen across?
2 ohm resistor.
2 ohm.
So V2 will be here. All right, good. So what I'm interested in is finding IX, yes, with respect to I1. So I1 will pass through the 4 ohm. See that? And
Yes,
it will
sir.
divide between the 2 and the 3. And whatever goes through the 3 will go through the 2. All right? So it is current division between 2 and 5. So we get 2I1 over 7, which means that V2 would be 4I1 over 7. Remember, you don't have to redraw this. You have it already. Everybody cool with this? This means, therefore, that Z21 is 4 over 7. Now, is there anything special about the network?
Symmetrical.
Yes, sir. Symmetrical.
Huh?
Symmetrical, sir.
Symmetrical.
Symmetrical. Thank you. So because it is symmetrical, it means that we immediately know the values of Z22 and Z12. So that's our impedance matrix. Again, I use the same symmetry to speed up my analysis for the admittance parameters. But there are my that's my network. We put in our short circuit. Yes. With the short circuit, the 4 ohm now comes into play. So looking in, yes, we get ZT. All right. So ZT, that's the resistance equation or the impedance equation, and that's a simplification. So we get 1 over ZT to be 19 over 102. Hopefully now you will have a better appreciation for the use of the resistance equation. All right. Now that we have Y11, because we already have port 2 short circuited, we can then find Y21. Why do I write the stone or just state the register? So we're using voltage divider. Yes. But bear in mind, students, we already have these impedances at the various stages. Yes. So it makes application of the voltage divider quite simple, because wherever we have a plus sign, we'll use voltage divider. So we want Vx and Vy. In finding Vy, that will be the voltage across the 2 ohm and the 4 ohm. So I can then find I2 from that. All right, and so Vx, again, we are using the impedances that we had calculated before. All right, let me just pull up the participants list and mark the names. Blackboard. Present, sir. Beckford, Dario Beckford. Yeah, sorry about that. Do we have this?
Yes.
All right, and then I can find VY. Again, we already have the voltages, the impedances, so we can just manipulate that. So it means that Y21 is minus 2 over 102. Again, because it is symmetrical, yes, we therefore have Y12 and Y21. And what I want you to do is to use the conversion matrix and convert the impedance parameters. Make sure you get the admittance. All right? Okay. Yeah, I'm pretty short on time. My bad planning today. But anyway, Atkins, I know you are here. Beckford. Dario.
Yes, sir.
Bigger staff. Bigger staff. Simeon. Black is here. Blackwood. Adrian. All right. Bora. Brown. Imani. Brian is absent. Cameron. Janelle.
Yes, sir.
Campbell. Renee.
I'm here.
Sounds up today. Anyway, Cahoon.
Present.
Dixon is here.